If you can trace the graph of a function f on an interval ab continuously, we say that f is continuous on the interval ab. Here's an example. We can easily trace the graph of this function on the interval ab, which means for the values that are greater than a and less than b. Because we can do so, we conclude that f is continuous on the interval ab. So how come a function is not continuous on the interval ab? Here's one example. Now there is no way to trace this graph of this function continuously when x is greater than a and less than b, because there is a gap. We say that this function is discontinuous on the interval ab. In this case, we can also look and see that there is no limit at x equals c. Here is a beautiful continuous function on the interval ab, but now I'm taking the point at which x equals c and I give it another value of the y. In this case, the function is again discontinuous on the interval ab because you cannot trace it continuously because there's a little gap. But in this case, the limit at x equals c exists. It is easy to inspect the graphs for continuity. We just have to trace the graph, and we cannot do it and we have to jump over, then it means that the function is not continuous at that value of the x. For example, we are going to inspect this graph at x equals -2, x equals 3, and x equals 10. We even want to do more. We also want to inspect not only continuity, but also to pay attention to the limits. Let's start with x equals -2. You can observe that the right limit is 5, the left limit is -4, the limit when x approaches -2 does not exist, and you can see easily that the function is discontinuous at x equals -2. What about x equals 3? The right limit and the left limit are both 3. It means that the limit of the function is 3, and the function is still discontinuous at x equals 3 because we have to jump on this little tiny hole at x equals 3. Now let's inspect x equals 10. The limit from the right and the left equals 1, so the limit exists and equals 1, and the function is also continuous at x equals 10. In this case, there was no limit and the function was not continuous. In this case, there was a limit and the function was discontinuous. We have this situation. We really like to find out what is the connection between having a limit and being continuous, or maybe discontinuous. Here is the official definition of being continuous. A function f is continuous at x equals c if the limit of the function when x approaches c equals to f of c. So there is really a very strong connection between having a limit and being continuous, because part of being continuous is having a limit. The limit of the function x approaches to c have to exist, but even more, it has to be equal to the value of the function at that point. We have also those not very useful definitions, so I'm just going to give it to you, but I'm not going to use it. We say that the function is continuous from the right of x equals c if the limit of the function when x approaches to c from the right equals f of c. And the matching definition is obviously a function that is continuous from the left of x equals c. In this case, the limit of the function when x approaching to c from the left equals to the value of the function at x equals c. Definition. This is an important definition. A function f is continuous on the interval ab if it is continuous for any number between a and b. Now we want to dig more into this very important definition of a function to be continuous. So the definition says that first of all there is a limit, which means we have 1, the limit of the function when x approaches c from the right exists, and 2, also the limit of the function when x approaches to c from the left exists. But if there is a limit, we know that the limit from the left and the right has to be the same, but even more. Their common value is L. If you put 1, 2, 3 together, we already know that the limit of the function when x approaches c equals L. This is a good example of this situation. Observe the graph of this function. The limit from the left and right exists, and also they are the same. But this is not enough for continuous. Continuous is more than having a limit. Limit is only about what we are expecting to have. A function is continuous if we also have what we expect to have. We're really expecting this dot there to be filled in. We are expecting that the value of the function at c, f of c, equals L. Here is our expectation that this dot is there. And we have that. We say indeed that the function is continuous at x equals c. There is also a different way to view this. So let's see. First of all, if the function is continuous at x equals c, then x equals c has to be in the domain of the function, which means that f of c exists. So we know that there is something there. There is some value for the function at x equals c. But this is not enough. We also have to be able to trace the graph from left to right and right to left there, which means that it has to be that the limit from the right at x equals c is f of c, which means we must have this part, and also we must have the other part because we should be able to trace from left and right of x equals c on the graph. It means that also the limit from the left side of c exists. And obviously if you put this together, you get again the main issue here that the limit of the function when x approaches to c equals f of c. We realize then that if a function is continuous at x equals c, then we have those 4 conditions. 1. The limit of the functions when x approaches to c from the right exists. The limit of the function when x approaches to c from the left exists. The limits in 1 and 2 are the same, and their common value is L, which means that the limit of the function when x approaches to c is L. And condition 4, that L equals to the value of the function at x equals c. Now we are getting 2 theorems which are the direct result of this. First one. If f(x) is continuous at x equals c, then the limit of the function when x approaches to c exists. Let's see what this theorem means. The condition of this theorem that the function is continuous at x equals c, which means we have 1, 2, 3, and 4. Then it is telling us that the limit exists. For limit, you need only to check 1, 2, 3. So this theorem actually claims that if you have 1, 2, 3, 4 as above, then you have 1, 2, 3 as above. But this is clear that if I have all these 4 conditions, then I have also these 3 conditions, and these 3 conditions are promising me that the limit of the function when x approaches c exists. But also another theorem, if the limit of the function when x approaches c does not exist, then the function is discontinuous at x equals c. Again, this is the direct result of the 1, 2, 3, 4 above. The condition of this theorem is that the limit does not exist. Limit does not exist, it means that 1 or 2 or 3 fails. But if 1 or 2 or 3 fails, then 1, 2, 3, 4 fails.